This is you. This is your computer. You know C++, but your computer speaks in only ones and zeros. This means that we need some sort of translator between our language and the computer's language. This is our compiler. Our compiler is the function that takes in a string of text in C++ or another language and outputs another string of text in some lower level language. Since this is a function, we can implement our compiler as a program in another language. Here is a thought experiment. We can implement the Rust compiler in the same language, Rust. We first implement a compiler for Rust in a different language, like C++, and get an executable compiler. Then we use this executable to write a Rust compiler in Rust. Beware that if we do this, bugs written in the first pass compiler will be hidden and not caught by the Rust compiler. As if our first compiler had errors, but we only look at the source code from the second compiler, we may never find errors in the first pass compiler. This has strong implications. It means that we can never fully trust our compiler to be correct. So compilers often don't compile directly to the machine target language. This is because we have different CPU architectures that have different sets of instructions. Instead, compilers often compile to some intermediate language like LLVM, and those get turned into the machine language. This has the advantage of we only have to implement optimizations for one intermediate language, and different languages can share the same intermediate representation. So here, C++, Rust, and Zig all use LLVM. Modern compilers use multi-level intermediate representations. This is because optimizations done on lower-level items, such as registers, are different from optimizations done on higher-level items, such as loops. There is also something known as interpretation, where instead of compiling our entire program to a machine language in one function call, we execute our program line by line. This is done by an interpreter, which is also another program, that executes the instruction of a program directly, without compiling it to machine code. There also exists something called just-in-time compilation, where instead of compiling our program to machine language in one call, we compile line by line. This is done with a just-in-time compiler, which compiles our code on the fly and can cache different compilation steps. Inside our compiler, we have 3 steps. First, there's a lexer that converts our C++ token into a sequence of tokens. Then a parser converts the tokens into something called an abstract syntax tree, which is a tree from the syntax of our code. Then we end with a generator that traverses this tree and generates code for each node in the tree.